Right now, inside a Huawei facility in Dongguan, there's a machine being powered up for the first real trial run of its life. Not a simulation, not a lab bench test. An actual attempt to fire a laser that generates the exact wavelength of light needed to print the world's most advanced computer chips. ASML's own CEO said building this from scratch would take China many, many years. That trial run is happening this quarter. Let that timing sink in for a second, because it's the entire reason this story is worth 15 minutes of your time instead of 30 seconds of scrolling past a headline. This isn't a 5-year government roadmap slide promising something down the road. This isn't a research paper describing future ambitions. This is happening on a factory floor right now while you're watching this video. And almost nobody outside a small circle of chip industry analysts has actually connected what that timing means yet. Here's the number that should genuinely stop you before anything else. The laser system inside ASML's real machine, the one company on Earth that's ever gotten this technology to actually work commercially, contains 457,329 individual parts. That's not the whole machine. That's just the laser subsystem. China is trying to fire up its own version of that exact system right now, using a fraction of the R&D time and money ASML spent building the original. So is this actually happening? Or is this getting oversold the same way half the China breakthrough headlines do? Stay with me, because there's a specific detail about 2 minutes from now that tells you exactly how real this trial run actually is. And it's not what most coverage of this story is reporting. Let's start with why this laser is even the hard part, because almost nobody explains this clearly. ASML's machine works by firing an extremely powerful carbon dioxide laser at tiny droplets of molten tin, each one smaller than the width of a human hair, roughly 50,000 times every single second, vaporizing each droplet into a plasma that emits ultraviolet light at exactly 13.5 nanometers. Hit the droplet wrong, even slightly, and you get nothing usable. The laser has to strike each droplet twice in rapid succession, once to flatten it into the right shape, then again to actually vaporize it, all timed with nanometer-level precision, continuously, for years of factory use without failing. That entire subsystem, the one built from over 457,000 parts, comes from 2 specific companies. Germany's Trumpf builds the high-power CO2 laser itself. A San Diego firm called Cymer, which ASML acquired back in 2013, builds the surrounding light source module around it. 2 companies. Decades of specialized engineering. That's what it actually took to make this laser reliable enough to sell. Think about what that actually implies for anyone trying to replicate it from a standing start. It's not one difficult component sitting inside an otherwise simple machine. It's an entire specialized industry, spread across 2 countries and 2 separate companies, each one solving problems the other one couldn't, refined over roughly 3 decades of continuous engineering. Anyone attempting to shortcut that timeline isn't just trying to build a laser. They're trying to compress 2 entire companies' worth of accumulated expertise into a fraction of the time it originally took. China's approach skips the CO2 laser entirely. According to multiple reports, 2 separate Chinese research teams have been racing toward their own version of this exact light source, using solid-state lasers instead. A fundamentally different design that ASML itself reportedly abandoned years ago for not being efficient enough at commercial scale. One team, led by a scientist named Lin Nan, who previously worked inside ASML's own light source division before returning to China, now operates out of Beihang University. The other, led by Professor Zhao Yongpeng at Harbin Institute of Technology, has been developing a separate method entirely, called laser-induced discharge plasma, which vaporizes tin between electrodes instead of hitting droplets directly with a beam. Notice what's happening structurally here too. because it's the same pattern that keeps showing up across China's broader chip strategy. Rather than betting everything on a single approach and a single team, the effort is deliberately split across two competing methods, run by two separate institutions, essentially hedging the entire national bet across multiple chances at success instead of one. It's a more expensive way to attack a problem. It's also, historically, often a faster one. Here's the detail that actually connects this straight to the Dongguan trial run happening right now. According to reporting this year, Huawei's own facility has been specifically designated as the primary testing site for these first production units, with trial runs scheduled for this exact quarter. That's not a future promise. That's not a 5-year roadmap slide in a government presentation. That's a live, current, active test, happening at almost the exact moment this video is being published. Sit with that timing for a moment, because it changes how you should read every number that comes after it in this video. A trial run happening this quarter means whatever data comes out of Dongguan over the next few weeks is going to either validate or quietly undercut everything both Chinese research teams have published so far. This isn't a story you're catching up on after the fact. It's one where the actual proof is still being generated as you're watching this. It's also worth understanding what a trial run at a facility like this actually involves in practice, because it's not as simple as flipping a switch and watching the laser turn on for the first time ever. By the time a system reaches a live trial run stage, the underlying physics has already been proven in smaller lab setups, sometimes repeatedly, over months or years. What a trial run at scale actually tests is whether the system holds up outside a controlled research environment, under real factory conditions, with real vibration, real temperature swings, and real continuous operation instead of a single carefully staged demonstration. That's a genuinely different and genuinely harder bar to clear than simply proving a concept works once in a lab. If breaking a story down while it's still actually unfolding, instead of waiting for the dust to settle and repeating what every other channel already said, is what you want more of, subscribing right now means you're actually watching this story develop in close to real time, not catching up on it months later. Now here's where the honest scorecard actually starts, because the specific word impossible in this video's title deserves real scrutiny, not just repetition. ASML's own chief executive, on a live investor call earlier this year, said it's always possible to generate some EUV light, but that building a full working machine around it would take China many, many years. That's a real quote, and it's worth being precise about it, because it's not quite the flat impossible the headlines are throwing around. It's closer to a confident, specific prediction about timeline, made by the one person on Earth with the most authority to make it, and made before either Chinese team had published their results publicly. Here's what actually happened next. Reporting from the Diplomat and multiple other outlets has since confirmed that China's light source efforts have reached a conversion efficiency of roughly 3.42%, genuinely ahead of the top European research lab working on this exact problem, which had only reached 3.2% as of 2019. And on power output specifically, both Chinese approaches are currently sitting somewhere between 100 and 150 watts. Here's why that number actually matters more than it sounds like it should. ASML's own light source hit 250 watts back in 2017, enough to process 125 wafers an hour, and has since climbed to a 600-watt commercial benchmark, with a 1,000-watt system already announced for this year. China hasn't caught ASML's current output. It hasn't even caught ASML's output from 9 years ago. Put those two numbers side by side, and the honest picture gets a lot clearer. 3.42% conversion efficiency beating a European research benchmark is a genuine scientific win. 150 watts sitting well below a power level ASML cleared nearly a decade ago is a genuine reality check. Both of those facts are true about the same laser at the same time, and that's precisely why neither the breathless headline nor the dismissive one-liner actually captures what's happening here. So here's the honest answer to the actual question in this video's title. Did China fire up an EUV laser ASML said was impossible? Yes, in the narrow, literal sense, both Chinese teams have generated real, usable EUV light at the correct wavelength, using their own domestically developed methods. That part genuinely happened, and it happened faster than most Western analysts expected. But the machine still isn't running at anywhere close to the power level needed for real commercial chip production, and reaching that level isn't a matter of turning a dial higher. It's an entirely separate engineering problem involving heat, efficiency losses, and component durability that ASML itself spent additional years solving, even after its own laser first worked at all. There's also a detail buried in this story that deserves way more attention than it's gotten. Both Chinese teams reportedly rely on solid-state lasers, specifically because pursuing ASML's original CO2 laser approach from scratch would have taken even longer. That means China isn't just trying to copy ASML's homework. It's genuinely attempting a different solution to the same underlying physics problem, one ASML itself walked away from years ago. If that different approach actually works at commercial scale eventually, it wouldn't just be catching up to ASML's specific machine. It would be proving there was more than one valid path to this technology all along, something the 25 years of ASML's total monopoly had quietly convinced most of the industry wasn't true. That distinction matters for a reason that goes beyond national pride or competitive bragging rights, too. If solid-state lasers eventually prove viable at commercial scale, it opens the door for other countries and other companies to attempt EUV lithography using an entirely different, potentially cheaper technology base than the one ASML spent 30 years perfecting. A monopoly built entirely around one specific engineering approach is only as secure as the assumption that no other approach could ever work. China's teams are currently the biggest test of whether that assumption actually holds up. Watch what actually comes out of Dongguan this quarter, because a successful trial run doesn't need to hit commercial power levels to be meaningful. It just needs to prove the system runs reliably enough to justify the next round of investment and engineering. Watch the power output specifically over the coming months, because closing the gap from roughly 150 watts toward that 250-watt threshold ASML cleared back in 2017 is the real signpost that separates a lab curiosity from an actual manufacturing roadmap. And watch whether China's two competing teams, Lin Nan's group and Zhao Yongpeng's group, eventually combine their efforts or keep racing each other, because right now resources and talent are still split across two different approaches instead of one unified push. There's also a component of this story that rarely makes it into the headlines, and it's worth understanding before you decide how big this trial run actually is. A working laser, even a perfect one, doesn't turn into working chips on its own. That light still has to bounce through an entire chain of ultra-precise mirrors before it ever reaches a silicon wafer, and separate reporting on China's broader EUV program indicates that piece, the optics chain, remains significantly further behind than the laser itself. Some accounts describe China's mirror system as relying on domestically manufactured components paired with artificial intelligence-powered correction software, specifically to compensate for precision the physical hardware can't yet match on its own. That means even a flawless trial run in Dongguan this quarter only solves roughly 1/3 of the actual machine. The laser generates the light. the optics chain has to deliver it with atomic-level precision. And an entirely separate wafer stage has to hold the silicon perfectly still, down to fractions of a nanometer, while all of that happens. 3 enormous engineering problems, and the one being tested this quarter is arguably the one China has made the most progress on so far. That's actually the more useful way to think about this entire story. It's not one machine that either works or doesn't. It's 3 separate, nearly impossible problems being solved on 3 separate timelines by teams that may not even be fully coordinated with each other. The laser being fired up in Dongguan this quarter is a genuine milestone in exactly one of those 3 problems, and understanding which one keeps you from either overreacting or dismissing this the moment the next headline shows up. There's a bigger question sitting underneath all of this too, one that goes past whether this specific laser succeeds or fails. Reporting suggests this entire effort has drawn something in the range of $37 billion in investment and involves thousands of engineers coordinated in what people close to the program have compared to China's own version of the Manhattan Project. That's not the language people use to describe a side project. That's the language of a government treating this specific choke point as close to the top of its national priority list, and pouring resources at a scale that eventually makes almost any engineering problem solvable. Even if the timeline stretches years longer than the most optimistic version of this story suggests. Compare that $37 billion figure to what ASML itself actually spent developing this technology the first time, and the scale gets even more striking. ASML's own EUV program is widely estimated to have cost somewhere around $8 to $10 billion over roughly 3 decades, spread across the company itself, along with direct co-investment from Intel, TSMC, and Samsung. China's program, by comparison, is reportedly being funded at several times that level, compressed into a fraction of the time. Money alone doesn't guarantee a breakthrough. Engineering problems don't simply dissolve because you throw more funding at them, but it does dramatically change how many parallel approaches, how many recruited engineers, and how many simultaneous experiments a program can actually run at once. And that's precisely the kind of brute force advantage that turns a 5-year problem into something closer to a 2-year one, at least on paper. Drop one word right now before you go anywhere. Sparked. If you think this trial run genuinely proves ASML's monopoly has a real ticking expiration date. Stalled. If you think a laser stuck at 9-year-old power levels isn't the breakthrough the headline wants you to believe. Type it now. Then go watch exactly how far behind China's mirror and optics technology actually is compared to this laser, because that piece of the machine is moving at a completely different speed, and it changes what any of this power output actually means for a real working chip.